All right, hello, welcome to the first video for Unit 3. So we are making our way through the course, and we have finally arrived at Unit 3. This is a long unit with very important concepts at play. The unit title is called Intermolecular Forces and Properties, and in Topic 1 here we're just going to be sort of introducing the intermolecular forces that we're going to be talking about. So, here is the exam and course and exam description, I should say. The learning objective, I'm not going to get into every little detail here, but I will highlight some of the big things. Okay, so right here, the enduring understanding, intermolecular forces can explain the physical properties of a material. Very true. And that's going to be a huge theme for us starting today and moving forward throughout this unit. We're going to be talking about the relative strengths of intermolecular forces, how you can identify what intermolecular forces are going to be there, their relative strengths, and then what kinds of physical properties arise from those intermolecular forces. So that's sort of, you can of course read all of these little pieces of essential knowledge, but that's sort of the bulk of what we're going to be getting into, right? Identifying what intermolecular forces there are, determining their relative strength, and then being able to discuss how physical properties arise from those intermolecular forces, the presence of those intermolecular forces. Okay, so table of contents here. We're going to be talking about dipole-dipole forces, hydrogen bonding, and London dispersion forces. So these are the three big types of intermolecular forces we're going to be talking about. This is from Chapter 10 in your book. We're going to be talking a little bit about melting and boiling points. These would be physical properties, right? So we're going to be connecting some dots here. And I've left this problem-solving blank because, this is kind of an introductory day, so I'm not sure exactly what types of problems we're going to be solving. We will have a problem set, of course, but the problems might sort of be all over the place. And so we're going to be tackling a lot of the problem solving together in class. So there won't be a separate problem solving video. We'll sort of just tackle some of the problems together in class. Okay, I've stolen this slide from the 2.2 notes, actually, the difference between intra and intermolecular forces. In Unit 2, we talked about intramolecular forces. These were covalent bonds and ionic bonds. These are things that hold individual molecules together, right? That hold atoms together into units. What we're going to be getting into this unit are the intermolecular forces. Intermolecular forces are the forces that occur between molecules, okay? And so we will discuss these later in the course. Well, that's right now, all right? So that's what we're getting into today. All right, so first type of intermolecular force is generally referred to as a dipole-dipole force, or a dipole-dipole interaction, okay? Many molecules which contain polar covalent bonds have net dipole moments. So think of water, ammonia, okay? Things that are, asymmetric, right, in terms of their molecular geometry, and also have those polar covalent bonds. Those molecules, right, have net dipole moments, and we consider those to be polar molecules. Okay? These polar molecules have partially positively charged regions and partially negatively charged regions. In the solid and liquid states, where molecules are in close proximity to one another, right? So either they're in a solid where they're sort of packed real close together in sort of a regular fashion, like a crystal structure, for example, or in a liquid where they're sort of mingling together but still in close proximity. In both of those cases, the polar regions of molecules can electrostatically interact with each other, meaning the positive and negatively charged regions can be attracted towards one another, right? Or positive and positive, or negative and negative, can be repelled away from each other, okay? Molecules will arrange themselves in a solid or liquid state to maximize those attractive forces and minimize those repulsive forces, just like how in ionic bonding, and actually, I should say now, ionic compounds actually are dipole-dipole interactions, okay, so positive, negative. So just how in those crystal structures, how they were arranging themselves to maximize the attractive forces and minimize the repulsive forces. Same thing happens with polar molecules, okay? So these intermolecular forces are called dipole-dipole forces, when you have positive and negative regions that are, attracted and or repelled away from one another. A big important dipole-dipole force, okay, so this is kind of a subset of dipole-dipole forces, are called hydrogen bonds, okay? So most dipole-dipole forces tend to be only about 1% of the strength of ionic or covalent bonds. But a particularly strong type, so maybe slightly more than 1%, a particularly strong type of dipole-dipole force is called hydrogen bonding. And if you were in my class last year, I know we talked about this a little bit. Hydrogen bonding is this occurs whenever hydrogen bonds to a particularly electronegative atom. So nitrogen, oxygen, or fluorine are what the typical atoms are that arise in hydrogen bonding. So great example of this is water, okay? So you have a hydrogen, which has an electronegativity of 2.1, covalently bonded with an oxygen, electronegativity of 3.5. That's a difference in electronegativity of 1.4. And so this is a very polar covalent bond. Water is sort of has this asymmetric structure to it, right? We can draw this line of symmetry here. So what we can see, like in this water molecule here in the center, the hydrogen, due to having the lower electronegativity, is partially positive on both ends there. The oxygen is partially negative. What hydrogen bonding is, it is the intermolecular force, the dipole-dipole force, the interaction between one water molecule and neighboring water molecules. Okay, so they are attracted towards one another. And you'll notice here that the way that this is drawn, like this partially positive region is sort of oriented towards the partially negative region, and that's how things behave in real life. Okay, so water molecules, like I said on the last slide, in a glass full of liquid water, the water molecules are moving around, but they're always trying to sort of maximize those attractive forces and minimize those repulsive forces. Okay, so strong interactions occur between water molecules. It's really hard to overstate the importance of hydrogen bonding in chemistry and biology. Okay, and it's particularly prevalent in solid and liquid water. Okay, and this is mainly getting to biology. It is important in chemistry, obviously, but it's mainly important in biology. Solid and liquid water exhibit really, really unique properties due to the ubiquitous hydrogen bonding that occurs between all of the molecules. As we look at this picture here, hydrogen bonding is all over the place. In fact, that's the only real type of intermolecular force that's going on between water molecules. And hydrogen bonding is particularly strong in terms of all of the different types of intermolecular forces. So the really, really strong intermolecular forces that water exhibits, or that water contains, result in some very unique properties, as opposed to other liquids and other covalent solids that exist. So water has really high adhesion and cohesion and surface tension, extraordinarily high melting and boiling points, a really high specific heat capacity, and its density happens to be lower as a solid than as a liquid, which results in ice floating. All of these are a result of hydrogen bonding. We don't have the time right at this moment to sort of get into all of these in nitty-gritty detail. I may be giving you like a link to a video or two that'll explain this in a little bit more detail. But it is important to know that water does have its unique properties due to the hydrogen bonding that's present. Okay, so dipole-dipole forces, or interactions, that's one big category. Another category of intermolecular forces are called London dispersion forces, sometimes just referred to as dispersion forces. These are relatively weak intermolecular forces, and I think this diagram here is the best way that I can show you what a dispersion force is. Okay? So in this first stage, by the way, these are two different scenarios here. This scenario here on the left is not supposed to represent this scenario on the right. These are two atoms, whereas these are two molecules. So let me concentrate over here on the left side first. In atom A and atom B, who knows what these atoms are? They could be hydrogen, they could be, fluorine, they could be uranium, it doesn't matter. in these two atoms here, we've got some electron density, or some negative charge that is, around the nucleus. All right, this is one way to sort of model the quantum nature of electrons, right? So in this case here, we have no polarization. All right. What naturally occurs due to the random nature of how electrons behave, and just how all things behave, right? Due to the random nature that the way electrons behave, you can end up with slight, brief, instantaneous dipoles that sort of arise due to the random movements of the electrons. Okay, so take a look here. In the first scenario here, in this first picture, the electron density is sort of evenly distributed around the nucleus. What can happen, and what does happen, okay, we have like empirical proof of this, what does happen from time to time, brief instantaneous moments, is that the electrons just happen to be sort of weighted in a probability type of perspective, weighted on one side of the nucleus rather than the other, okay? And so what you end up with is kind of a higher electron density on one side of the nucleus, or one side of the atom, compared to the other. This is called an instantaneous dipole, okay? So we have an instantaneous dipole. What this means is that we have a partially negative region, right? Electrons are negatively charged. A partially negative region on the left side of the molecule, and a partially positive region on the right side of the molecule. These are instantaneous dipoles they're not permanent. They just sort of arise due to the random nature of electron movement. What can then happen, and what does happen, is the instantaneous dipole can induce a similar dipole in neighboring atoms, okay? And so we end up with, since this is a partially negative region, partially positive region, this partially positive region sort of attracts the electrons in neighboring atoms, and so you end up with sort of a similar looking type of instantaneous dipole that exists in neighboring atoms. So we have an instantaneous dipole that sort of arises due to the random nature of electrons, and then we have induced dipoles. Okay, induced just means sort of caused. Induced dipoles in neighboring atoms that happen due to the random nature of the electron movement in the first one. Okay, so what ends up happening then is you have a slight interaction here, right? Positive and negative. You have a slight sort of interaction, slight attraction that occurs between atom A and atom B. This is weaker than dipole-dipole. Okay? In dipole-dipole interactions, these partially positive and partially negative regions are permanent. Okay? They're partially positive and partially negative due to the difference in electronegativity. Dispersion forces can occur in non-polar molecules and in atoms of noble gases, for example, where there's no bonding at all. Okay? So these dispersion forces are sort of temporary, but they do impact the properties of these substances to a lesser extent, though, than dipole-dipole forces. Okay, so dispersion forces, or London dispersion forces, are weaker intermolecular forces, but they are there, and they do influence the properties in substances like nonpolar substances and noble gases. Okay, so the strength of these dispersion forces depends on a couple of different factors. The amount of contact area. Okay, so you'll see here, like, if two atoms have a lot of contact area, then these dispersion forces can sort of have more ability to influence each other. There can be like more inductions of these dipoles. If there's less contact area, then there can't be as much induction of the dipoles. The big thing, though, okay, is number 2, the polarizability of atoms and molecules. Basically, what this means is if you have atoms or molecules that have a lot of electrons, then that atom or molecule is more polarizable, okay, it's more susceptible to this sort of process than a smaller atom that has fewer electrons, okay? So more electrons means more polarizability in the context of these dispersion forces. So what this means is that if you were comparing two atoms, a big atom and a small atom, the bigger atom would have more propensity or more availability for there to be larger dispersion forces than in the smaller atom. Okay, and that's due to the larger amount, or the more electrons present in the system than in the smaller atom. Okay? All right, so intermolecular forces strongly influence properties of substances, and with the two that we're going to talk about right now are melting and boiling points. Okay? A general rule is that substances with relatively strong intermolecular forces tend to have higher melting and boiling points. Okay? Why? Let's think about that. Okay? So, first of all, think about what it means to be solid, liquid, or gas. Right? To be a solid, all the molecules are sort of locked in place. Right? You would think of them as being strongly interacting. Right? If they weren't interacting with each other, locking themselves into place, they could be free to move around. But they're not, right? So in a solid, there's very strong interactions between the different atoms or molecules. In a liquid, the molecules are still sort of staying together. They have the freedom to move around, but they're still sort of staying together in the same, volume, right? They're not flying off by themselves. That would be a gas, right? So once again, in a solid, you're going to have really strong interactions. In a liquid, you're going to have sort of moderate interactions, the strong to moderate interactions, and in a gas you're going to have like no interactions, right? The molecules are flying off by themselves, rarely coming into contact with each other. If they're not coming into contact with each other, then they're not interacting, right? So substances with relatively strong intermolecular forces tend to have high melting and boiling points. They have to get really hot. You have to put in a lot of energy to get them to move from the solid to liquid state, or to move from the liquid to gaseous state. And what I'm trying to get you to see here is the reason why, right? It is those intermolecular forces. That is the explanation, really, right? If individual atoms and molecules are strongly interacting with each other, they require more energy to separate. And that's really what the difference is between a solid, liquid, and a gas. It's the separation of the molecules and atoms. Pure ionic compounds that are made of positive ions and negative ions, right? Cations and anions. Pure ionic compounds have the strongest dipole-dipole interactions that exist. Okay? We're talking about, +1, +2, +3 potentially, right? Charges on those cations, -1, -2, -3 charges on those anions. Strong ionic interactions, okay? Coulombic electrostatic interactions. Those really, really strong interactions keep ionic compounds as solids at extremely high temperatures, okay? Pure ionic compounds have some of the highest melting and boiling points of all known substances, okay? And it's because of those really, really strong interactions. Noble gases, which don't bond at all, okay? There's no bonding going on with, as we've seen in the previous chapter, or the previous unit, you can make some compounds with noble gases, but not many. So noble gases, which generally don't bond, the only intermolecular forces that can occur in noble gases are going to be those weak dispersion forces, right? Those like temporary dipoles and induced dipoles. Noble gases, okay, very, very weak interactions, have some of the lowest melting and boiling points of all known substances. Okay? And that's because, right, it doesn't take much energy to get them to fly off apart from one another, because they're not interacting with each other. Even if they're packed together in a solid, they're very cold. It does not take much energy to get them to fly off. They're not interacting with each other much, even if they're in that solid form. Okay, so this list is it's not a, this list is, generally speaking, the relative strength of intermolecular forces, okay? It's not always going to be exactly in this order, but this is a rough general rule that you can sort of follow, okay? The strongest intermolecular forces are going to be dipole-dipole interactions between between ions, okay? Whole numbered charges, okay? So think of sodium chloride, right? Or magnesium phosphate, okay? If you've got ions that have whole number charges, +1, -1, for example, or +2, -2, the dipole-dipole interactions between those ions is really, really strong, Okay, so that is sort of number one on the list. And sometimes we don't really think of this as being an intermolecular force. Sometimes you think of this as being an intramolecular force, right? Ionic bonding. But at the end of the day, it is a dipole-dipole force. So I've included it here on this list. That's definitely going to be your strongest type of intermolecular force. Next strongest would be a dipole-dipole interaction. These would be like hydrogen bonds, okay? These are going to be strong partial positive or partial negative regions, okay? These occur when hydrogen covalently bonds with a very electronegative element, like nitrogen, oxygen, or fluorine, and you end up with, very strong partial positive and partial negative regions, like in water, for example, okay? Next down your list is, once again, dipole-dipole interactions. These are going to be other polar covalent situations, okay? So these are weak or moderate partial positive or partial negative regions. This might be carbon and oxygen bonded together. Not going to be as strong as a hydrogen bond, but the difference in electronegativity between carbon and oxygen is sufficient enough to have a polar covalent bond. And so if you have a compound or a molecule that has a carbon-oxygen bond, that's going to be a polarized region, or those are going to be polarized regions. And so the interactions between, one atom of formaldehyde, for example, which has a carbon-oxygen double bond, and another, there is going to be some interaction there. It's just not going to be as strong as a hydrogen bonding situation. And then lastly, you get to those London dispersion forces. Okay, these are those weak, brief dipoles and induced dipoles. The strength of these dispersion forces depends on that contact area and the number of total electrons available. Okay, these tend to be your weakest intermolecular forces. Okay, those general rules allow us to make predictions about, this just say relative, about relative melting and boiling points, okay? But they are general rules. The reality of certain substances can break those rules, okay? So it's not something that you can strictly adhere to, but it can give you enough information to make some predictions. If you're presented with some data, however, we have to be able to think critically to try to explain what's going on. So let's look at these three examples here. So the first molecule is Bi3. First of all, this breaks the octet rule, right? Boron is capable of doing that. We have a trigonal planar structure, okay? So boron and iodine, let me take a look at my electronegativity chart here. This is not going to be a very polar covalent bond, plus this is a trigonal planar structure. So this would be a symmetrical situation. So this is a non-polar molecule, okay? So it's a non-polar molecule. That means the only potential intermolecular forces that we're going to encounter are those London dispersion forces, which are the weakest type of forces, right? So we have the weakest type of forces here present in boron triiodide. Next compound is phosphorus trichloride. This and ammonia are actually very similar compounds in terms of their structure. These are both trigonal pyramidal, okay? And if we look at the difference in electronegativity, these both have a difference in electronegativity of 0.9. So phosphorus to chlorine is a difference of 0.9, and nitrogen and hydrogen is a difference of 0.9. So these are both containing polar covalent bonds, and they're both asymmetrical, right? They both have that trigonal pyramidal shape, right, where you've got that lone pair of electrons on top. So we have dipole-dipole forces present here, as well as the potential for those London dispersion forces. Now, what we just said was that hydrogen bonding is like your strongest type of intermolecular force, right? Notwithstanding the ionic situation, okay? So hydrogen bonding, which would be here, right, nitrogen and hydrogen, we would expect for nitrogen and hydrogen that hydrogen bonding situation, we would expect for that compound to actually have the highest boiling point, but it does not. Okay, it actually has the lowest boiling point of these three. And we would also expect, right, phosphorus and chlorine, which is sort of this other polar covalent situation, we would expect this, which is a stronger interaction than the London dispersion forces, according to this list, we would expect phosphorus trichloride to have a higher boiling point than a, non-polar molecule, like boron triiodide. But it has a lower boiling point than that does. So what's going on here? Well, this is just a really good example of how this list is a general rule, but it's not, something that you can strictly adhere to, okay? Here's the reality. Boron, and particularly iodine, because actually boron isn't very big, but iodine is a huge atom, okay, atomic number 53, and we have 3 of them, okay? That's over 150 electrons that are present in this molecule, okay? The sheer number of electrons that are present here causes the London dispersion forces to actually have a huge impact, okay? Remember how the dispersion forces depend on the number of electrons available. The polarizability of the molecule depends on the total number of electrons available. 150 plus electrons here. So the London dispersion forces that are present in this molecule are actually really strong when you compare it to, say, a very, very tiny molecule like ammonia. NH3, the total number of electrons here is like 10, okay? So this molecule here is beating ammonia by a factor of 15 in terms of the total number of electrons. So even though this is the most polar molecule down here, the total sort of sum of the intermolecular forces is actually weaker, much weaker, than in boron triiodide's case, okay? And it's kind of the similar situation here in the middle. Chlorine is, phosphorus and chlorine are both bigger than nitrogen and hydrogen. So even though they have sort of equal, they're equal in terms of their polarity and their structure, it's the increased size of the molecules, right? We have about 100 or 110 electrons here compared to just 10. And so by a factor of 10, we have more electrons present here. So those London dispersion forces, despite being weak in nature, just the sheer number of electrons sort of outweighs that polar factor, okay, and that hydrogen bonding factor, okay? So all I need you to understand, okay, in terms of comparing these forces, is that this is a general rule, but it's not always true, and you have to sort of investigate everything about the compounds, their polar covalent bonds, if any, the number of electrons present, like are we talking about big atoms here, small atoms here, and we can make educated guesses about their properties, like their melting and boiling points based on that. Okay, so like I said, we'll definitely work on some problems together in class. Definitely need a little bit more time to sort of break all of this down. And like I said, this is kind of like an introductory day to these intermolecular forces. We're definitely going to be investigating these more as the unit goes on. All right, thanks for watching, and I'll see you in class.